Okay, this is part 2, looking at section 3.2, measures of dispersion. We're talking about standard deviations, variances, ranges, and we ended off on the last video finding the range of the bottled water and the tap water, and so we can see that there was more range, or more dispersion based off of the range in the tap water of 0.59 compared to 0.26 in the bottled. Now the next one is which water has more dispersion in pH using the standard deviation as that measure. So to find our standard deviation, again I've got the information here in StatCrunch, and just as a reminder how we got this, so you're going to go under the stat menu, and then you're going to go summary stats by column. I'm going to make sure I highlight both of these, so I'm going to hold the shift key, and then the standard deviation is highlighted right here. I do want to note this is a sample, but if you need a population standard deviation, when you come down here, the unadjusted standard deviation, so I'll put that in the mix there too by holding on a Mac. I held the command key. On a PC, I believe you hold the control key, and that will keep everything else and add in the unadjusted standard deviation. Remember, this is a population standard deviation or population variance. So that's what this unadjusted means. If you just choose variance and standard deviation, those will be samples. So please note that. Okay, so when I come in here, you can see the standard deviations for both, and here are the unadjusted. They should be a little bit different. So the standard deviation for the tap water is 0.153, or around to 0.154. And then for the bottled water, we're 0.081. Sorry, I'm writing this on my iPad over here. So we can see that there's more dispersion in the tap water compared to the bottled water when we look at the standard deviations as well. So sometimes I'll put SD for standard deviation. So again, that standard deviation just helps us get an idea of kind of the average distance or spread of these data points, how spread out we are. So, okay, now we're going to look at a concept called the empirical rule that has to do with standard deviations. Okay, now first thing with the empirical rule, if the data have a distribution that is bell-shaped or symmetric, well, bell-shaped, which is symmetric, okay, then we can apply this idea called the empirical rule to determine the percentage of data that will lie within k standard deviations of the mean. So within 1 standard deviation, 2 or 3, and that's where it applies, is 1, 2, and 3. So if we are roughly bell-shaped, then approximately 68% of the data will lie within 1 standard deviation of the mean. So that is to say that approximately 68% of the data will be between the mean minus 1 standard deviation and the mean plus 1 standard deviation. Okay, then approximately 95% of the data will be within 2 standard deviations. So you would subtract 2 standard deviations from the mean, add 2 standard deviations to the mean, and approximately 90% of your data will lie within that range. And then the 99.7% will be within 3 standard deviations of the mean. Again, that's below and above together. So sometimes people will remember this as the 68, 95, 99.7 rule, but this is the empirical rule. Again, it's an approximation. It's not exact, but when we get into the actual details later on in the course, we'll see that this is a pretty good approximation. Okay. Now, please note that the empirical rule is that we can also base it on the sample data, x bar, and just use x bar in place of the mean mu and s in the place of the standard deviation sigma. So we can apply this to a sample, it doesn't necessarily have to be the entire population. So here's kind of a picture to help. So if we are within one standard deviation, so this is one standard deviation above and below. So that range right there, all of this area under the curve, would represent approximately 68% of the data, or 34% would be to the left, so between one standard deviation below and the mean, and then 34% to the right, because it's symmetric, so we can take that 68 and cut it in half. Okay, that's one standard deviation. Okay, and then if we go out to 2 standard deviations here, above and below the mean, then under that curve, okay, all of this area right here will be 95% when we add all of those little percentages up. And so 95% of your data is going to lie within 2 standard deviations of the mean. Or if you cut it in half, you would have 34 plus 13.5, which is 47.5. So you'd have 47.5 between the mean and 2 standard deviations below the mean, and 47.5 between the mean and 2 standard deviations above the mean. Okay, just a different way to look at it. Okay, and then the 99.7 rule is if you go out 3 standard deviations, which is pretty much all of your bell curve. Okay, you're going to capture 99.7% approximately of your data. And so then at that point, you're only missing 0.3% that's above or below the 3 standard deviation threshold. So if you're more than 3 standard deviations away from the mean on a bell curve, it's a very abnormal result, is another way of thinking of it. So just remember the 99.7, the 68, 95, 99.7 rule. Okay, we're going to look at a question here with the empirical rule. So we have the following data represent the weight in grams of a random sample of 50 M&M plain candies. So all of these represent a single observation. Okay, and the first question is determine the sample standard deviation of the weight and express your answer rounded to 3 decimal places. So what we're going to do here, I've got all of these weights pulled up here in StatCrunch, so we're going to go over to Stat, Summary Stats again by column. I'm going to pick my weight, and my standard deviation is highlighted, so I'll compute. So my standard deviation to 3 decimal places is 0.036. Okay, and so we're going to be 0.036 standard will represent 1 standard deviation. So right here is 0.036, and that was in grams. Okay. So I'm writing on my iPad. Didn't have it for you. Sorry about that. So then, on the basis of a histogram that was drawn in section 3.1 in a certain problem, we want to comment on the appropriateness of using the empirical rule to make any general statements about the weight. Okay, here is what the histogram looks like. You can see it's not perfectly bell-shaped, but we do have this big cluster in the middle, and then it kind of tails off, and so you can see that, I mean, you could roughly create a little bell-shaped curve out of that. And the mean and the median are kind of right lined up there. If you wanted to generate that in StatCrunch, you'd go under your graph, create a histogram, and compute. Okay, this one's a little bit different because the class widths are a little bit they're a little bit different than that picture as far as what was generated by StatCrunch. But again, if I were to come in here and if I were to add in the mean and the median, you can see that those things are super close. And so we feel very comfortable about this being bell-shaped approximately. Okay. So for part B, we're just gonna kind of do a check there. Part C says use the empirical rule to determine the percentage of M&Ms with weights between 0.803 and 0.947 grams. Okay, so and we note that X bar is 0.875. So if we take a look at this and we do 0.875 plus 1 standard deviation, 0.036, okay, that's going to give us 0.911. So that's 1 standard deviation above. 0.875 plus 0.036, or excuse me, minus 0.036 is 0.839. So that's 1 standard deviation. So I'll just put a note here. This is 1 standard deviation above and below. Okay, but that doesn't quite grab the 0.083 and the 0.947. So if I do 0.875 minus 2 times 0.036, okay, that will give me 0.803. And then if I do 0.875 plus 2 times 0.036, that will give me the 0.947. So part C is 2 standard deviations. 2 standard deviations. Or I should say within 2 standard deviations is what this question is asking. So within 2 standard deviations of the mean. Okay, so since we are within 2 standard deviations of the mean, then this tells us that 95% of the data will be, approximately 95% of the data will be within 0.803 and 0.947. Just as a note, 68% will be between 0.839 and 0.911, just as a note there from the empirical rule. But to answer that question C, 95% of the data will be within 0.803 and 0.947. Okay. And then part D, what it wants us to do is it wants us to determine the actual percent of M&Ms that weigh between 0.803 and 0.947 grams inclusive. So if you come over into StatCrunch, you can sort this and you can check and count how many of these are within that range. So between 0.803 and 0.947. And if you look, there's only 2 that actually fall outside of that range. And so in part D here, 48 out of the 50 are within 2 standard deviations when we count it up, and that is 0.96 or 96%. So again, we say approximately based off of the empirical rule, and then we look at the actual data, it is 96%, so you can see they're very close. So the estimate is pretty good on that. Okay, part E wants us to use the empirical rule to determine the percentage of M&Ms with weights more than 0.911 grams. Okay, so if we're more than 0.911, remember 0.911 is 2 standard deviations above the mean. And so if I come back up to my picture here, okay, then 2 standard deviations is right here.